Aligning large language models with human preferences has traditionally relied on reinforcement learning from human feedback, or RLHF. While powerful, RLHF is a notoriously complex and unstable multi-stage process. First, we perform supervised fine-tuning. Then, we train a separate reward model on pairwise comparisons. Finally, we optimize the policy using proximal policy optimization, or PPO. This third stage is the bottleneck. It requires keeping 4 neural networks in GPU memory simultaneously: the policy, the reference model, the reward model, and the value network. Tuning hyperparameters is a dark art, and training is highly sensitive to policy collapse. Is there a way to bypass this complexity and optimize preferences directly? To understand how we can simplify alignment, we must examine the mathematical foundation of human preference learning, the Bradley-Terry model. This model assumes there is an unobserved, latent reward function, R. When presented with a prompt, X, and 2 candidate responses, y_w and y_l, the probability that a human prefers y_w over y_l is modeled using the sigmoid function of the difference between their respective rewards. This means that a response with a higher reward is exponentially more likely to be preferred. Standard RLHF uses this formulation to train the reward model via maximum likelihood estimation. But what if we could mathematically rewrite this relation to avoid training a reward model altogether? Direct preference optimization, or DPO, achieves this through an elegant mathematical substitution. Under the standard RL optimization objective, which maximizes reward while penalizing deviation from the reference policy via Kuhlback-Leibler divergence, there exists a closed-form analytical solution. This identity expresses the optimal reward function in terms of the optimal policy, the reference policy, and an intractable partition function, z of x. Crucially, when we substitute this mathematical identity back into the Bradley-Terry preference model, the complex partition function, z of x, cancels out entirely. This is the core breakthrough of DPO. We can express the human preference probability directly in terms of policy likelihood ratios. By eliminating the latent reward term, DPO derives a simple, closed-form binary cross-entropy loss function. The DPO loss is optimized directly over the policy parameters theta relative to the reference policy theta ref. The loss is computed as the negative expectation over preferred and dispreferred pairs of the log sigmoid of beta times the log ratio of the policy ratios. In essence, the loss increases when the policy assigns a higher probability to the preferred response relative to the reference policy and decreases it for the dispreferred response. The gradient of this loss function acts as a dynamic vector field, scaling updates based on how incorrect the model's current preferences are. DPO represents a massive leap forward in model alignment. By eliminating the reward model and the unstable PPO loop, DPO reduces GPU memory requirements, cuts training times by more than half, and removes the need for complex reinforcement learning hyperparameter tuning. This direct optimization technique is now a standard pillar in aligning state-of-the-art models like Llama, Mistral, and Gemma. For more deep dives into the elegant mathematics and hardware mechanics driving modern AI, subscribe to Gemini 3.5 Flash Model. Let's keep optimizing the future of computation.